Off the coast of Oregon, roughly 300 miles out into the open Pacific, the ground just moved. A magnitude 4.9 earthquake struck along one of the most seismically active fault zones in North America. A fault that, according to Oregon State University's own analysis, produces more earthquakes than the infamous San Andreas Fault in California. Within hours, seismologists at the Pacific Northwest Seismic Network and the USGS were combing through the data, and headlines were already starting to ask the question that comes up every single time the ground shakes anywhere near the Pacific Northwest coastline. Is this it? Is this the beginning of the big one everyone's been warned about? Here's the honest answer, and it's more interesting than a simple yes or no. This earthquake almost certainly has nothing to do with the megathrust fault capable of producing a magnitude 9.0 event, the one we've covered in detail before. But that doesn't mean it's meaningless, and it doesn't mean scientists are shrugging it off either. There's a real reason this fault gets watched as closely as it does, and understanding why requires untangling two completely different fault systems that sit uncomfortably close to each other off the Oregon coast, systems that get confused constantly, including by people who really should know better. Today we're breaking down exactly what fault this earthquake actually occurred on, why it's genuinely one of the most active earthquake zones in North America, why scientists are watching it closely without being alarmed by it, and how it relates, or more accurately, doesn't relate, to the Cascadia subduction zone, sitting just a couple hundred miles closer to shore. No exaggeration, no false alarm, just what the seismology actually tells us. Before we get into it, I want to ask you something a little different this time. Have you ever felt an earthquake and had no idea what fault it actually came from, or whether you should be worried? Drop a comment and tell me, because I think this confusion, mixing up which fault did what, is honestly one of the most common and most avoidable sources of public panic in earthquake coverage, and today's story is a perfect example of exactly that. And if you want to keep getting accurate breakdowns of seismic activity as it happens, instead of panic headlines, subscribe to the channel. It's completely free and it helps enormously. A thumbs up goes a long way too. Let's push this one to 6,000 likes so it reaches people who actually want the real explanation instead of the scary version. All right, let's get into it. To understand what just happened off the Oregon coast, you need to understand that there are actually two entirely separate, geologically unrelated fault systems sitting in roughly the same stretch of ocean. And almost every earthquake headline out of this region gets more confusing than it needs to be because people conflate the two. The first, and the one most people have actually heard of, is the Cascadia subduction zone. This is the megathrust fault we broke down in detail in an earlier video, the one where the Juan de Fuca plate is being forced underneath the North American plate, locked in place, accumulating stress for the past 326 years since its last full rupture in the year 1700. Cascadia sits relatively close to shore, generally within 50 to 100 miles of the coastline, and it's the fault capable of producing that catastrophic magnitude 8.7 to 9.2 earthquake scenario, along with a fast-arriving, devastating tsunami. The second fault, the one this week's magnitude 4.9 earthquake actually occurred on, is called the Blanco fracture zone, and it is a fundamentally different type of fault, doing a fundamentally different thing, sitting much farther out to sea. The Blanco fracture zone runs roughly 220 miles in a northwest to southeast line, starting about 150 kilometers off Cape Blanco, Oregon, and extending out toward the Juan de Fuca Ridge. Geologically, it's what's called a transform fault, the exact same category of fault as California's San Andreas. That means the motion along this fault is horizontal, two blocks of oceanic crust grinding sideways past each other, rather than one plate diving underneath another the way it does at Cascadia. The Blanco zone connects two seafloor spreading centers, the Gorda Ridge to the south and the Juan de Fuca Ridge to the north, essentially acting as the connective hinge between two places where new ocean floor is being created. This distinction, transform versus subduction, isn't just seismology trivia. It's the single most important fact for understanding why this earthquake matters far less than a headline number like 4.9 might suggest on its own. Here's something that surprises a lot of people the first time they hear it. The Blanco fracture zone isn't just active, it's one of the most seismically active locations in the entire continental United States. And by some measures, it actually outproduces the San Andreas Fault in raw earthquake frequency. Oregon State University researchers, tracking data going back to the 1970s, have documented more than 1,500 earthquakes of magnitude 4.0 or greater along this single fault zone. That's an extraordinary number for a fault most people have never even heard of. The reason comes down to the mechanics of what the fault is actually doing. The Blanco zone accommodates the relative motion between two spreading ridges moving at different rates, with the western segment sliding at around 1.4 centimeters per year, and the eastern segment moving nearly 3 times faster, at close to 3.9 centimeters annually. That differential movement, plus the fault's role connecting two zones of active seafloor spreading, means stress builds up and releases along this fault constantly in a steady, ongoing rhythm rather than the centuries-long silent buildup we see at Cascadia. This has produced some genuinely dramatic earthquake swarms in recent memory, and this week's magnitude 4.9 fits into a pattern seismologists have watched play out repeatedly. In December 2021, an intense swarm hit the Blanco zone, with 88 separate earthquakes recorded in a span of just a few days, 15 of them magnitude 5.0 or greater, with the two largest reaching magnitude 5.8. In June 2022, another swarm produced 9 earthquakes in quick succession, topping out at magnitude 5.6. A magnitude 6.0 struck the same general area in January of this year, and a magnitude 6.3, matching an earlier 2019 event, has also been recorded along this fault. Now, researchers studying the zone have documented at least 133 earthquakes of magnitude 5.0 or greater here since 1980 alone. Read that last part again. More than 130 earthquakes above magnitude 5.0 in roughly 4 decades on a single fault, and not one of them has ever been followed by a destructive earthquake on land. That track record is exactly why seismologists respond to a Blanco zone earthquake with careful, methodical monitoring rather than alarm. It's not that they're ignoring it, it's that decades of consistent data tell them precisely what this type of event does and doesn't lead to. This is probably the single most important practical fact buried in all of this, and it comes directly down to the mechanics of a transform fault versus a subduction zone. Tsunamis are generated by vertical seafloor displacement. When a subduction zone ruptures, one plate is jolted upward while the seafloor above it lurches, physically displacing an enormous column of ocean water all at once, which is what generates a tsunami wave. That's exactly the mechanism behind the catastrophic scenario at Cascadia, and it's why a Cascadia rupture could send a wave to the coastline in under 20 minutes. A transform fault like the Blanco zone doesn't work that way at all. The motion is side to side, not up and down. 2 blocks of crust are sliding horizontally past each other, which means there's essentially no meaningful vertical displacement of the seafloor, and therefore no meaningful mechanism to generate a tsunami wave, even during a fairly large earthquake on this fault. USGS research geologists studying the zone have been direct about this, explaining that tsunamis form where you get significant uplift on one side of a fault or the other, and that lateral, sideways motion, like what happens at Blanco, simply isn't the kind of movement that produces one system. It's the direct, well-understood consequence of what kind of fault this actually is. If the Blanco zone doesn't produce tsunamis, and rarely, if ever, produces damaging shaking on land, given how far offshore it sits, a fair question is why seismologists pay it any on the proximity question. The Blanco fracture zone sits roughly 200 miles west of the Cascadia subduction zone, and geologists have been extremely clear on this point when asked directly. The two fault systems are mechanically distinct and effectively unable to trigger one another. As one geologist put it plainly when asked whether a Blanco zone swarm could set off a Cascadia rupture, the chances of that happening are considered almost impossible. Different fault type, different stress orientation, different depth, and enough physical distance between them that the kind of stress transfer that can sometimes trigger nearby faults in other tectonic settings essentially doesn't apply here. That's the reassuring part. But here's the part that actually justifies the close monitoring. Every earthquake anywhere along the Pacific Northwest margin, including ones on a fault as seemingly disconnected as Blanco, gets folded into a much larger data set that seismic networks use to understand the overall stress state of the region. Earthquake monitoring isn't just about predicting the next big one on a single named fault. It's about building the most complete possible picture of how an entire tectonic margin is behaving in real time. A swarm on Blanco gives researchers data on regional stress patterns, helps calibrate the sensitivity and accuracy of detection networks, and occasionally reveals genuinely new science about how the Juan de Fuca and Gorda plates are deforming as they get squeezed and pulled in different directions by the larger tectonic forces acting on this stretch of ocean floor. There's also a simple, practical reason seismic networks respond quickly and publicly every time this happens. Public reassurance is only credible if it comes paired with real transparency. When a magnitude 4.9, or a larger swarm like the one in 2021, with earthquakes up to magnitude 5.8, occurs on a fault capable of producing measurable shaking that some coastal residents genuinely feel, the responsible move for scientists is to explain clearly and immediately what's happening, rather than letting silence get filled in by speculation. That's exactly what happened this week, with seismic networks publishing rapid explainer analysis within hours of the earthquake, walking through the exact same distinction we're covering right now. Transform fault, no tsunami risk, historically not associated with triggering the subduction zone. It's worth pausing on why a magnitude 4.9, nearly 300 miles offshore, generates headlines in concerned comment sections in the first place. Because it's not really about the earthquake itself. It's about geography and memory. The Pacific Northwest has spent the better part of the last decade absorbing a genuinely well-deserved wave of public education about the Cascadia subduction zone, its 326-year silence, its overdue status relative to the historical rupture average, and the sobering FEMA modeling suggesting the region west of Interstate 5 could be functionally devastated in a full margin rupture. That awareness campaign worked. People in Portland, Seattle, and along the Oregon and Washington coastlines now generally know this threat exists in a way that simply wasn't true a generation ago. But awareness without precise geological literacy creates its own problem. When any earthquake happens anywhere off the Oregon or Washington coast, a lot of people's mental model collapses the entire offshore region into a single, undifferentiated danger zone, somewhere out there where the big one is supposed to happen. A magnitude 4.9, nearly 300 miles out on a completely different non-threatening fault type, gets processed through that same anxious framework, even though the actual seismology couldn't be more different from a Cascadia event. This is genuinely one of those more useful things good earthquake reporting can do, not amplify the fear, but sharpen the picture. A magnitude 4.9 on the Blanco fracture zone and a hypothetical magnitude 4.9 on the Cascadia megathrust itself would represent two almost entirely different categories of event, with different implications, different associated risks, and different reasons to care about them at all. Precision here isn't pedantic. It's the difference between accurately understanding your actual risk and needlessly living with a low hum of misplaced anxiety every time the ground shakes anywhere near the coast. Since we're being precise about this, it's worth laying out what seismologists would actually consider a meaningfully different, more concerning signal, because the answer helps clarify why this week's earthquake doesn't rise to that level. A genuinely concerning development on the Cascadia subduction zone itself would look categorically different from a Blanco zone. Swarm. Scientists monitoring Cascadia watch for things like unusual patterns of slow slip events, a phenomenon where the locked portion of the megathrust releases stress gradually over days or weeks rather than suddenly, detectable through dense GPS networks that track millimeter-scale ground deformation along the coast. They watch for any cluster of small earthquakes occurring directly on the shallow, locked interface of the subduction zone itself, rather than on a separate, well-mapped transform fault sitting 200 miles further offshore. And critically, they watch for any earthquake, regardless of size, that occurs close enough to shore and shallow enough to actually generate measurable vertical seafloor displacement, since that's the actual mechanical prerequisite for tsunami generation, not simply the magnitude number by itself. None of those specific markers are present in this week's event. It occurred on a well-documented, well-characterized transform fault with a 4-decade track record of similar-sized events producing no destructive consequences on land. It occurred far enough offshore that even the shaking itself was only reported as felt by a small number of people directly along the coast, if any at all. And it's consistent, both in magnitude and location, with dozens of comparable events on the exact same fault segment stretching back to the 1970s. This is, in the most literal sense, exactly what normal expected seismic behavior along an active transform fault looks like. Not a false alarm being ignored, but a well-understood phenomenon being correctly categorized. It's worth taking a moment to appreciate just how much infrastructure sits behind a headline like magnitude 4.9 earthquake off Oregon, because the speed and confidence with which scientists were able to characterize this event, fault type, depth, tsunami risk, historical context, all within hours, is itself a genuine scientific achievement built over decades. The Pacific Northwest Seismic Network, jointly run by the University of Washington and University of Oregon, operates a dense array of seismometers across the region, feeding continuous data to the USGS's National Earthquake Information Center. When an offshore earthquake occurs, multiple stations detect the seismic waves at slightly different times, and triangulation across that network allows scientists to pinpoint location, depth, and magnitude typically within minutes, even for events happening hundreds of miles out at sea. Because the nearest seismic stations to a Blanco zone earthquake sit roughly 300 miles away on land, precisely locating the depth of smaller events is genuinely difficult, which is part of why USGS listings for this region often default to a standard 10-kilometer depth estimate for shallow offshore events, an acknowledged limitation of monitoring something this far from land-based instruments. The same network feeds directly into Shake Alert, the West Coast earthquake early warning system we've discussed before in the context of a full Cascadia scenario. For an event like this week's magnitude 4.9, occurring far offshore and well below the threshold where early warning alerts typically get pushed to the public, the system's main function was simply rapid and accurate characterization, confirming quickly and publicly that this was a Blanco zone event, not a Cascadia event, and that no tsunami threat existed. That combination, dense instrumentation plus rapid, transparent public communication, is exactly the kind of infrastructure that separates a region that responds to uncertainty with information from one that responds with either false reassurance or unwarranted panic. It's the same infrastructure story we've told before with Japan's early warning network, just operating at a smaller scale for a smaller event on a fault most people have genuinely never heard of before this week. If you're in the region, here's the practical takeaway, and it's less about this specific earthquake and more about how to process the next one, because there will be a next one, probably sooner than you'd expect, given how frequently this fault produces activity. First, learn to recognize the language scientists use to distinguish these events, because it tells you almost everything you need to know at a glance. An earthquake described as occurring on the Blanco fracture zone, roughly 200 to 300 miles offshore, is fundamentally a different category of event from anything described as occurring on the Cascadia subduction zone or characterized as a megathrust event. If official sources explicitly state there is no tsunami threat, as they did again this week, that assessment is coming from an understanding of the fault's actual mechanics, not a guess. Second, don't let the frequency of Blanco zone activity create either complacency or fatigue about the very real, separate risk posed by Cascadia. These are not competing signals that cancel each other out. The Blanco zone producing a swarm doesn't make Cascadia any less overdue. Any more than a quiet month on Blanco would mean Cascadia's risk had somehow decreased. They are genuinely and provably independent systems. And your actual preparedness planning, tsunami evacuation routes, emergency supplies, knowing your zone should be built entirely around the Cascadia risk profile we covered previously, regardless of what the Blanco zone happens to be doing on a given week. Third, if you did feel this week's earthquake, or any earthquake in the region going forward, take the 30 seconds to submit a Did You Feel It report through the USGS website. This isn't just a formality. Citizen-submitted felt reports genuinely help scientists refine shaking intensity maps, particularly for offshore events where instrumented data alone can't fully capture how the shaking actually propagated and was experienced on land. Here's what's worth sitting with as we wrap this one up. A magnitude 4.9 earthquake off the Oregon coast this week is a genuinely normal, well-understood event on a fault that produces this kind of activity with remarkable regularity, and has done so for as long as scientists have been keeping detailed records. It tells us essentially nothing new about the Cascadia subduction zone, doesn't raise the risk of a tsunami, and fits cleanly into a 4-decade pattern of similar events, on the exact same fault that have never once translated into anything destructive on land. But the fact that it generated headlines and concerned questions anyway tells us something worth understanding about how we process geological risk in an era when the public has finally, appropriately, become aware of the far larger threat sitting nearby. Precision matters. Not because the Cascadia threat isn't real, it very much is, and we'd encourage you to go back and watch our full breakdown of exactly what that fault is capable of, but because conflating every tremor near a dangerous region with the worst-case scenario for that region doesn't make anyone safer. It just adds noise to signal, and it makes it harder to recognize what an actually concerning development would look like when, someday, one does occur. The Blanco fracture zone will almost certainly produce another swarm like this one before too long, possibly within months, possibly within a year or two, based purely on its own well-established rhythm. When it does, the responsible response isn't fear. It's the same thing scientists did this week, quickly, transparently, explaining exactly what fault moved, exactly what that means, and exactly what it doesn't mean, so that the region's genuine, hard-earned understanding of its real seismic risk stays sharp instead of getting blurred every time the ground shakes anywhere near the coast. We'll keep tracking every development along this margin, both the routine Blanco zone activity and any genuine changes in the Cascadia monitoring data. Subscribe so you don't miss any of it, and drop a comment letting me know if you're anywhere on the